Okay, before we finish up chapter 6, I thought we needed to step back a minute and think about mutations because the next part of chapter 6 is going to be looking at some things that will change in chromosomes, which are also mutations. A mutation is going to be any change in the underlying DNA structure that an individual started with. So one of these places that can happen is when you just do replication. So we went over replication in our review early in the semester, and so this is what is called a spontaneous mutation. So let's say we have a strand of DNA, and it would have complementary pairs. So it would have, its complementary pairs. And then during DNA replication, these two strands will split, and they will become the templates of two new strands. So let's rewrite that, showing the split. And so complementary base pairs will come into each. So on this one, we'll have complementary base pairs come in. And on this one also, we'll have complementary base pairs. And we will create from one strand of DNA two new strands. But on occasion, there are mistakes. For instance, something that can happen is just by chance, a thymine can fall into place here. Now this is a mistake. Now typically, DNA polymerase 1 will come through here and it'll go, oh, hey, you made a mistake here. We'll take that one out and we will put in the correct one. But there are times when DNA polymerase 1 does not catch its mistake, and then now this will persist in that cell line. So one new cell will get what you originally had, but one cell will now get the mutated form. Now what happens next time around is when these split, we now have a new configuration. This will now go back to a normal line because the complementary base pairs will come back in and you're back to the original. But in this line, these cells will now carry a mutation because now this is different from the original. We went from a CG line now to an AG line. Overall, DNA polymerase 1 is very good at catching these mistakes, but as time goes on, as you know, chance is just going to catch up with you. Errors in replication happen in about 1 in every 1 billion base pairs. But when you think about it, each cell has 6 billion base pairs. That means on average, each cell has a chance of making 6 mistakes each time it replicates. So over time, you're going to find that these are going to accumulate. All right. We can just have errors in replication. We can also have what are called tautogenic shifts. And this is when the complementary base pairings, if you don't have the right orientation of a particular base pair, it can actually cause a different pairing. So as we know, T will typically make a double bond with A, so thymine and adenine. And you can see this in figure 11.5. However, on a replication round, if you remember, A is a purine, which means it has 2 nitrogenous rings. It's going to look very similar to a G, which is also a purine. And if G is not in the right orientation, thymine can actually bond with it and make those hydrogen bonds as it would with its complementary pair, and it doesn't know it's making a mistake. So purines can look similar enough that you can actually fool the complementary pair. It doesn't have to just be that way. So we just said, we'll bond with T. Thymine, remember, is a pyrimidine. And so, same thing. A, if it's not in the right orientation, C could also slip in here, another pyrimidine. Pyrimidines, remember, have one nitrogenous ring in them. Therefore, they look similar enough that sometimes they can fool their complementary pair. When they do, that is called a tautogenic shift. All right. Those are things that are going on within the cells. You can also have environmental factors. And environmental factors can be either physical or chemical. And by physical, we mean radiation. So this can be UV, X-rays, cosmic rays. Most of these are typically at high doses lethal, but even small amounts can cause changes. Matter of fact, one of the biggest changes that happens with radiation, and this is what happens when you get sunburn, is that the cells in your skin, let's say this is a chain of DNA. So if you get too much UV on a particular place, you can actually get it to break. And then thymine likes to actually bind with other thymines. And so you can actually get this weird bubble. And now you form this bond here and you have this sort of bubble of DNA that is above it. Now a lot of times then, when you go to do DNA replication, guess what? It's going to ignore that bubble. We'll do DNA replication. All of a sudden, we've lost 4 base pairs. We've gone from something that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 base pairs to something that's now 1, 2, 3, 4, 5, 6, 7. That is a change. We have actually lost stuff. So this is a lot of times when you get too much exposure to UV or X-rays. Matter of fact, they say that you shouldn't go through the X-ray machine more than 3 times a year if you're at the airport. So that's what we mean, small doses. But what a lot of people don't realize is that your biggest exposure is actually in your house. Radon, as you can see in figure 11.8, is the largest source of physical radiation that you are exposed to. You should be exposed to less than 4 picocuries on average. That is considered a safe enough level. Remember, pico is 10 to the negative 12th. So we're talking very, very small amounts. Now, in Allegheny County, we actually have a high amount of radon that actually bubbles up from us. We are sitting on relatively large sources of uranium, and as uranium breaks down, one of the things it gives off is radon gas. So if you have not had your house tested for radon, please do. If you're ever buying a house, make sure you do radon testing because it is one of the biggest sources of radiation. I had a house, I looked at a house over on the south side, and we did radon testing in there. It ended up being at about 2.5 picocuries, so that was a safe enough amount. But if you have not, I highly recommend getting that checked out. All right, I said environmental factors can be physical or they can be chemical. And chemical ones are called mutagens. They're called mutagens because they can cause mutations. There's a couple ways that they can do that. One of them is called base analogs. So if you treat some of these nucleotides with a chemical, they will change their structure. For instance, if you are to treat cytosine with nitrous acid, it will in effect become a uracil. So if you think about it, you have C and G. They are complementary pairs, right? So C would typically bond with G. So now they undergo replication. C would still bond with my G here. My G would bond with a C here. Well, let's say that this particular C becomes exposed to nitric acid. Now, in a sense, this G is now bonded with a U. And when it undergoes replication, this G will still bond with a C, but now this U, which is in effect a T, will bond with an A. So once again, it's a cytosine molecule, but it's acting like a uracil molecule. So now the next iteration, this one will still bond with another T, and now this one will begin to bond with an A. What started off in this space was a C and G, but now along this line and along this line, we have a mutation because of a chemical exposure. This is the really sad part about our society right now. We have listed on our register about 100,000 different synthetic chemicals. Most of them have not been tested to see if they are mutagens, but they can have some serious consequences. So that's what we mean by a chemical altering another nucleotide. That's why it's called a base analog. It's similar to something else, and we've changed its chemical nature. And this can be seen in figure 11.7. Also, we can have chemical modifications of bases. Chemical modifications will, in a sense, do the same type of thing. When you change a nucleotide, and now the system thinks that it is a different nucleotide, you can get that same kind of consequence of it carrying through in a particular line of cells. Remember, mutations by themselves are mostly innocuous. 99.99% of all mutations cause no problems. It's that 0.01% that cause the problems. So you don't need a whole lot of chemicals out there, but because there's so many millions of people and you do so many different types of mitosis over time, you end up getting lots and lots of exposures, giving you the chance that you could then become, a particular line could become mutated. If a particular type becomes mutated, and it is in a particular region of the cell, for instance, and those genes that control growth, that is when you can possibly lead to tumors. And if those tumors begin to spread, that's when you can get to cancers.